So very, very broadly, it is a method to solve the equations governing a whole range of physics. It could be the physics of deformation, the physics of fluid flow, the physics of heat transfer, the physics of quantum mechanics. So if you look at a finite element representation of a building, you will see the building and you will see these blocks drawn on it. And each of them is referred to as an element. And they're finite of certain size. So people think that's what finite elements refers to. That's a convenient way to think about it. It actually turns out that the finite in finite elements refers to a certain mathematical property of the functions that are used to represent it and so on. We also study the beginnings of what people need to know in order to understand how waves propagate. And it turns out then that there are a number of other problems in physics which use the same equations. It doesn't automatically work for everything. But because of this mathematical structure, people like mathematicians have been able to go into situations and study situations where the garden variety finite element method does not work, but then develop more sophisticated finite element methods that do work for these sorts of situations. The aim of the course is to bring students to the point where they are able to write computer code to actually solve problems with the finite element method. And so a bulk of the assignments and activities are built around that. If they've never taken a class in finite elements, then this will show them what this code is supposed to be doing, how it takes the basic physics and turns it into equations which it solves. The potential societal impact, there's no way to measure this, I think, is that practicing engineers know more about the black box that they were otherwise using, and fewer bridges fall.